Hello and welcome to Tech Simplified TV. Today we are at the last episode of topics related to physical design in VLSI. After global and detailed routing, today we will talk about specialized routing. Some special nets require extra attention and different technique to route. In today's episode, we will talk about different techniques of special routing and clock tree routing. If you are interested, stay tuned and focus till the end of the video.
Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and specialized routing. This is the third episode in routing in physical design, and we have already covered global and detailed routing. Now it's time for specialized routing. Next, area routing, key objectives and optimization factors. Next, basic concept in clock networks. After that, delay in clock networks, clock skew and clock routing problems, modern clock tree synthesis techniques. This is the first slide on this topic. Next, another slide on modern clock tree synthesis techniques. And then MMM versus RGM. These are two methods. There is a comparison between them. Then modern clock tree synthesis techniques. This is the third slide on the topic, and clock skew optimization and power trade-off, first slide, and clock tree optimization and power trade-off, second slide. So these are the pointers we will discuss in our today's episode. We are done with this slide. Now let's move to the next slide. Design flow and specialized routing. This diagram we are using for last few episodes, and today also we will take reference of this one. Once the flow enters physical design, there are multiple steps like partitioning, chip planning, placement, clock tree synthesis, signal routing, and finally timing closure. So in signal routing, we have already covered global routing and detailed routing, and today it's time for specialized routing. In digital integrated circuit, first signal wires undergo global routing and then followed by detailed routing. We all know that. However, in certain designs such as analog circuits and printed circuit boards, that is PCBs, with gridless routing or trackless routing, this distinction is unnecessary. It doesn't need this. Similarly, older or smaller designs with one or two metal layers also fall into this category. For this type of routing, we take specialized routing. Now, when global and detailed routing are not handled separately, area routing is used to directly establish metal connections for signal routing. Unlike routing with multiple metal layers, area routing prioritizes minimizing wire crossing. Clock signals require special consideration. This is the basic about specialized routing. We are done with this slide, and now let's move to the next slide. Area routing, key objective and optimization factor. We have already mentioned about area routing. When there is a discrimination between global and detailed routing is not required. Overall, it's done by area routing. Objective, area routing aims to connect all net while bypassing global routing, operating within the available layout, pace, adhering to geometric and electrical constraints. So that is global routing. Minimize total routed length and number of vias, optimizing wear area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. So these are optimization goal. Minimize total routed length and number of vias, optimize wearing area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. Now, constraint considered. Technological constraint like number of routing layers, where with electrical constraint like signal integrity, coupling effects, geometric constraints like preferred routing direction, wear pitch, etc. So these are the constraints. What are in number of routing layers, where with these are technological constraint. Now, electrical constraint like signal integrity, coupling effects, and geometrical constraint like preferred routing direction, wear pitch. Three types of technological constraint, electrical constraint, and geometric constraint. Now, impact of net ordering. The sequence of net routing affects efficiency and runtime. Greedy wear length based routing can cause inefficiencies, and multi-pin net require careful decomposition and ordering. That is impact of net ordering. In which sequence net ordering is done that affect the efficiency and runtime, and greedy wear length based routing can cause inefficiencies. So now net and pin ordering strategies. Pin ordering use Steiner tree based algorithm to convert multi-pin nets into two-pin nets, sort pin locations by x coordinate, and connect from left to right using shortest path algorithm. And net ordering challenges, finding optimal net order is complex. N factorial possibilities are there. Now net ordering rules are there. Nets with larger aspect ratios are routed first. If aspect ratio is the same, the shorter net length is prioritized. If a net's pins are fully inside another net's bounding box, it is routed first. The net with fewer interfering pins in its bounding box is routed first. Ties are resolved based on total pin count inside the bounding box. These are the rules followed. So this diagram is showing there are two ways to connect this net. There are two ways. It can be routed this way, can be routed this way also. Now there are 4 nodes and 2 nets are mentioned, like A and A. This net can be connected this way, these two, and these can also be connected this way. It's shown 2 different ways of connection in both the diagrams. So we are done with this slide. We will move to the next slide. Basic concepts in clock networks. Most digital designs are synchronous, that is, computations occur in sync with the clock signal. The clock ensures that internal state variables and inputs are processed correctly through combinational logic, generating new outputs and state updates. The clock signal, often called the system's heartbeat, can be generated off-chip or by on-chip analog circuits like PLL and DLL. Its frequency may be divided or multiplied depending on the need of the different circuit blocks. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all parts of the circuit receive the clock simultaneously. So this is the main focus in case of clock tree. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all part of the circuit receive the clock simultaneously. Now, a clock routing problem involves connecting n+1 terminals. A clock routing solution consists of wire segments that connect all terminals, ensuring the signal from the source reaches every sink. This solution has 2 key aspects: topology and embedding. So clock routing problem involves connecting n+1 terminal, and clock routing solution consists of wire segments that connect all the terminals, ensuring that signal from source reaches every sink. This solution has 2 key aspects. One is topology and other one is embedding. Clock tree topology are rooted binary tree G with n leaves representing the sink's internal node include the source and any additional Steiner points, and embedding defines the exact physical placement of edges and internal nodes in the topology. Figure A illustrates a 6-sink clock tree instance. This is a 6-sink clock tree. There are 6 sinks, and figure B shows its connection topology. So connection topology, it's a rooted binary tree with n leaves. So S1, S2, S3, S4. There are n number of sinks, so n number of leaves. This is the clock tree topology. And embedding, figure C presents a possible embedded clock tree solution. It's a possible embedded clock tree like S0. From there, this connection is going like that. S0 to S1 and S2, that is U1, this one. Now U2, U3, U4. From S0, it's coming to U2. From there, U3 and U4. And from U4, S5 and S6. And U3, S3 and S4. So this is the embedded clock tree solution, and this is the clock tree topology. We are done with this slide. We will move to the next slide. Delay in clock networks. Signal delay is the time a signal takes to switch states, that is low to high or high to low, as it travels through a routing tree. It starts at logic gate outputs built from nonlinear transistor and moves through wires and vias, which add parasitic effects. We all know about parasitic effects of wires. In our interconnect series, we have discussed that parasitic effect in detail. Now, exact delay calculations are complex, so tools like SPICE or prime time are used for precise sign of delay measurement. However, place and route algorithms use approximate models such as linear and Elmore delay models. Linear delay model. In the linear delay model, signal delay between nodes I and J is proportional to the path length in the routing tree, independent of connection topology. The normalized linear delay between nodes U and W is sum of edge lengths along the path. On-chip wires have both resistance and capacitance, which increase with length due to RC effects where delay grows quadratically, which the linear model does not capture. Despite this, it remains useful in design tools, especially for older technologies with lower drive resistance and wider wires. Its simplicity makes it widely used in EDA software. Linear delay model, although it's a linear model, and when RC comes into play, the wire delay increases or grows quadratically. It's a quadratically increasing, and we are trying to model it through linear delay model. It's not appropriate, although it's a good assumption because it's a simple model and it's very useful for older technologies with lower drive resistance. And L-mode delay model, the L-mode delay model we have already discussed in interconnect series in the delay episode. The L-mode delay model provides a more accurate delay estimate by considering resistances and capacitances in the routing tree, especially for modern circuits with significant RC effect. Physical design tools use L-mode delay approximation for three key reasons. First, it considers the effect of off-path wire capacitance on sync delay. Second, it provides a good balance of accuracy and correlation with circuit simulator estimates. And third, it can be computed efficiently in linear time using two depth-first traversals, one to determine capacitance below each node and another to calculate delays from the source to each node. It's considered downstream and it's upstream. These are the leaf like a tree. Current flow from this direction to that direction and the current out this way. The calculation is done. We have already discussed in detail in our interconnect series. Link is provided in the description. You can take a look if you want the reference of L-mode delay model. Delay in clock network is basically calculated by linear delay model, which works quite efficiently for older nodes, and L-mode delay model is much more accurate approximation. We are done with this slide. We will move to the next slide. Clock skew. There is one episode, different delay types in VLSI. There also we have discussed about clock skew. Clock skew is a maximum difference in clock signal arrival times between sinks. So clock skew and clock routing problems. We have already discussed about clock skew in one episode called different types of delays in VLSI. Link of that episode is provided in the description. You can take reference of that episode also, although the perspective a little bit different there. Clock skew, this is maximum difference in clock signal arrival times between sinks. Since the clock signal should reach all sinks simultaneously, minimizing skew is crucial for circuit timing. Ideally, clock should reach every sink at the same time, although it doesn't happen because the signal takes finite time to travel through the wires. Local skew, the maximum difference in clock arrival times between related sinks that are sequentially adjacent, meaning there is a combinational logic path between them. Usually there is a clock, there is a sequential block, and then some combinational blocks are there, so it takes some time to travel. So local skew is the maximum difference in clock arrival times between related sinks, that is sinks that are sequentially adjacent, meaning there is a combinational logic part between them, that is local skew. And now global skew, the maximum difference in clock arrival times between any two sinks, whether related or not. It is difference between the shortest and longest source to sink path delays in the clock tree. In most cases, global skew is what is referred to as clock skew in design analysis. So that is a maximum. If that is the clock and there is the closest sink present is there and the farthest is here, the skew from these two, the time difference in reaching this sink and that sink would be different, and that is the maximum difference when it's reaching the shortest path, covering the shortest path and the longest source to sink path. Difference between these two delays in the clock tree, that is actually referred as clock skew in design analysis. That is a maximum clock skew, and that is global clock skew mentioned at clock skew. There are few clock routing problems, like modern low power clock network design integrates zero skew trees and relies on SPICE for accurate circuit simulation. Zero skew tree ZST problem. A ZST ensures that the clock signal reaches all sink at the same time. That is zero skew. No skew is there. Skew is defined using a delay estimate like linear or L-mode delay. Bounded skew tree or BST problem. While ZST are useful in theory, exact zero skew is not practical due to increased wire length leading to higher capacitance and manufacturing variance, which cause difference in wire resistance and capacitance. Instead, real world clock tree allowed a small skew skew within a given bound. So ideally zero skew is not possible. So a small skew within a given bound, that is bounded skew tree, is acceptable level. A skew with an acceptable level is approved or allowed. Now useful skew tree problem. In some cases, global skew control is unnecessary. Instead, the focus is on local skew between related flip-flops or latches. Enforcing strict global skew constraint can overcomplicate the problem. So in some cases, it's not necessary. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signals between flip-flops arrive neither too late nor too early. Double clocking by optimizing sync arrival times, the clock period P can be reduced, improving circuit performance. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signal between flip-flop arrive neither too late, that is zero clocking, or not too early, double clocking. By optimizing sync arrival times, the clock period P can be reduced, improving circuit performance. There are two diagrams, that is minimal clock period time 0 nanosecond at 0 nanosecond, and after 2 nanosecond it's reaching here. After 6 nanosecond is reaching FF3, third flip-flop. So minimum clock period P equal to 6 nanosecond with 0 skew. And here skew is a little bit adjusted, like there is a skew of 2 nanosecond and it's reaching, and this one has 2 nanosecond skew. So if between these FF1 and FF2 there is a skew happens because of a combinational logic path is there, and for this path if the signal takes 2 nanosecond, so here when it's reaching FF2 it's basically zero skew, and when it's reaching here in 6 nanosecond, so it's effectively becoming 4 nanosecond with 2 nanosecond skew. So minimum clock period becoming 4 nanosecond with 2 nanosecond skew. So we are done with this slide. We will move to the next slide. So now modern clock tree synthesis. This is the first slide on this topic. So clock trees are crucial in synchronous circuit design. Obviously everything needs clock signals. There have to be a clock tree and affecting both performance and power consumption. And a well-designed clock tree ensures low skew, delivering the clock signal to all sequential gates simultaneously. That's the requirement or the expectation from a well-designed clock tree. And after the initial tree construction, the clock tree goes through clock buffer insertion to strengthen the signal and skew optimization to further reduce timing variation. So that is the basic. Constructing tree with zero global skew. 5 early clock tree construction algorithms whose core ideas still influence modern EDA tools. These algorithms address different scenarios like builds a clock tree without considering exact sync positions, construct both the tree structure and physical layout simultaneously, and 3 is given a predefined topology determines its physical placement. So H-tree, the H-tree is a self-similar fractal structure that ensures exact zero skew due to its symmetry. It's built by recursively dividing a unit square. A central segment is placed through the root. 2 shorter perpendicular segments extend to the centers of 4 quadrants. This process continues until reaching all sinks. The H-tree is widely used for top-level clock distribution, but it has limitations like blockages can disrupt the pattern, irregular sync placement makes direct implementation difficult, and high routing cost. To reduce signal inflection, where tapering is used, where the width halves at each branching point. This is H-tree. H-tree has a symmetrical structure, although it has some cons, some downside. That's why where tapering is used, where width halves at each branching point. This is H-tree. We are done with this slide. We will move to the next slide. Modern clock tree synthesis. This is the second slide. Method of means and medians. The MMM algorithm proposed by Jackson, Srinivasan and Pu in 1990 improves on the H-tree by handling arbitrarily placed sinks. It follows a recursive approach like partition terminals into 2 equal subsets based on median. It's partitioning again, it's based on median. So these medians are connected again based on this median. It's divided in this way and this way and this way based on median. so many small rectangular blocks are there. This method is flexible and adapts to different sink distribution. While MMM can be simplified into an H-tree-like approach, it only minimizes skew heuristically. In the worst case, the longest source to sink path can be as large as the chip diameter, making the algorithm's effectiveness highly dependent on cut direction selection. And this is improvisation over H-tree. Although it has a downside, like effectiveness of the algorithm depends on the cut direction selection. Now, recursive geometric matching or RGM. The RGM algorithm introduced in 1991 is a bottom-up approach to clock tree construction, unlike the top-down MMM algorithm. How RGM works, the algorithm finds a minimum cost geometric matching of n/2 line segment, ensuring no two segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew between connected sinks. The n/2 tapping points from one stage serve as input for the next matching step. The process continues until the clock tree is fully constructed. So here, clock tree structure started from median, here opposite. Any two adjacent sinks. So here algorithm was little bit different, like the algorithm finds a minimum cost geometric matching of n/2 line segments, ensuring no two segments share an endpoint. No two segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew. So these 2 points are connected by this segment and these two segments are considered and they are connected. And in between there is a tapping point is found. These two segments are connected and there is a tapping point. So those tapping points, tapping point from one, there is a tapping point of these two, there is a tapping point of these two are connected. Now in these two between there is a tapping point and again tapping point from here. So these are connected like this, these are connected. Again these two are connected by this tapping point, these two sinks are connected by this tapping point, and these two tapping point are connected by another tapping point. This is the tapping point of these four final at this stage, and here these two, there is a tapping point, these two, there is a tapping point, and between these two tapping point there is another tapping point, and these tapping points are connected, and in between we find another tapping point and this tapping point, and here it means here meets here in another tapping point. It's a bottom-up approach and here it's top-down approach. So we are done with this slide and we will move to the next slide. Now let's take a look at the comparison of MMM and RGM. These four sinks and top-down approach, median is found here. Again, two medians are found this way. And here it's a connected segment and tapping point, and these two, this tapping point and this tapping point connected, and here this is the tapping point. So RGM improves clock tree balance and reduces wire length. So we can easily see wire length is reduced here compared to MMM. Above figure compares MMM and RGM for 4 sinks. If MMM selects a poor cut direction, RGM can cut wire length in half. However, like MMM, RGM does not ensure zero skew. If two subtrees have very different delays and their roots are matched, finding a zero skew tapping point may not be possible. This is the comparison between MMM and RGM. We are done with this slide. We will move to the modern clock tree synthesis. This is the third slide on the same topic. Exact zero skew algorithm and deferred merge embedding. These two different algorithms. Proposed in 1991, the exact zero skew algorithm improves upon RGM by ensuring precise skew balancing using Elmore delay model instead of the simpler linear model. It uses Elmore delay model. Key feature, it calculates exact zero skew tapping point using the Elmore delay model, leading to lower actual clock skew in real designs. When merging two subtrees with different sourcing delays, it adjusts wire length to equalize the delays. During merging, the zero skew tapping point is carefully placed along the matched segment. It equalizes the delay by adjusting the wire lengths. When two subtrees with different sourcing delays are merged, the algorithm adjusts wire lengths to equalize the delay, because when clock signal travels through wire, some delay also added there. During merging, the zero skew tapping point is carefully placed along the matched segment. So these two are subtrees and this is the tapping point. So this length is calculated accordingly to balance the skew. And another method is deferred merge embedding. The DME algorithm improves clock tree construction by delaying the selection of merging or tapping points for subtrees. Unlike earlier method that fix internal node locations early, DME optimally places these nodes later, ensuring minimal source to sink delay and minimal total tree cost. So how DME works, unlike MMM and RGM, which only require a set of sink location, DME needs a predefined tree topology as input. Key advantage, MMM, RGM, exact zero skew fix internal node positions too early, limiting flexibility, whereas DME ensures more optimal placement of internal nodes, leading to better clock tree performance. Deferred merge embedding and improvisation over the previous algorithms. So we are done with this slide. We will move to the next slide. Clock skew optimization and power trade-off. This is the first slide. Key challenges. Low clock skew is critical for high performance design. Clock networks consume significant power, requiring trade-offs between skew and capacitance. Accurate timing analysis is needed. All the simulations are time consuming. Closed form delay models are inaccurate. A common approach is to optimize using Elmore delay model and then fine tune with more accurate models. Now clock tree optimization steps. There are multiple steps in that. First is geometric clock tree construction. Initial clock buffer insertion, clock buffer sizing, wear sizing and wear snaking. So these steps account for process, voltage and temperature variations. Now, high-level skew optimization. Earlier, a single buffer was enough to drive the clock tree. Now, technology scaling, multiple buffers are required. Buffer insertion ensures that clock signal reaches all sink efficiently. And Ginneken's algorithm optimally buffers a tree to minimize Elmore delay that runs in n squared time, quadratic relation, and where n is number of buffer locations, and a faster O(n log n) variant improves scalability. Optimizations reduce skew, power consumption and variability effect. So skew optimization is very important. Now clock buffer sizing. Initial buffer sizes impact later optimizations. Best size is determined experimentally, that is binary search. To fix skew between two sinks S1 and S2, identify the unique path between them. Upsize buffers based on pre-computed tables, and larger buffers improve robustness but increase power and delay. That is about clock buffer sizing. So now clock skew optimization and power trade-off. This is the second slide. This is a diagram. We have already used it in variability episode. So here process level, device level, circuit level and chip level variability factors are mentioned. So wear sizing, wear width affects power and manufacturing variation. Wider wears are more resilient to variation, although the capacitance and power consumption both are higher. Thinner wears are used in low power designs where width can be adjusted dynamically based on timing analysis. Now low level skew optimization focuses on local adjustment with higher precision. Techniques wear sizing, that is adjust width for fine-tuned timing. Wear snaking, that is increase path length through delay fast signals. Wear detouring increases capacitance and resistance, so that slows down the propagation. Now variation modeling. Process variation impact each transistor differently. Environmental factors, that is temperature, voltage fluctuation, affect performance. Now two modeling approaches are there for Monte Carlo simulation, that is accurate but slow, and pre-computed lookup table, efficient and reusable. Captures worst case skew variation based on technology node, bufferware library and path length, variation model, yield, etc. That enables fast, accurate optimizations, that is buffer sizing. And what are advanced clocking techniques? Active de-skewing and clock meshes, that is common in CPUs, and clock gating reduces power dissipation. These are advanced clocking techniques. We already have an episode on clock gating. Link is mentioned in the description. You can take reference if required. That is about specialized routing and clock tree routing. We are done with this slide and we are done with our today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any dislike, please put it as a comment. If you have a question or query, also put it as a comment. Thank you again and bye for today.